In this session of the reactions of alkynes, we will learn about the reduction of these compounds, how to reduce alkynes, and what kinds of products are obtained if alkynes are reduced. We learned before about the reduction of alkenes, and that alkenes can be reduced by hydrogenation reactions to give the corresponding alkanes. To take an unsaturated alkene to a saturated alkane by hydrogenation, which employed hydrogen gas and a metal catalyst such as palladium on carbon. In this lecture, we will learn about the reduction of alkynes, okay? But we will begin with what we begin with usually, which is terminal alkynes. So this is the structure of terminal alkynes. This is a terminal alkyne where the carbon-carbon triple bond is at the terminus. Now, if you take a terminal alkyne and you subject it to the same hydrogenation reaction conditions that alkenes have gone to, if you like, or that the alkenes undergo or react with, then the corresponding alkane will be obtained. Yeah? So a terminal alkyne, if treated with hydrogen gas in the presence of palladium on carbon as a metal catalyst, then the corresponding alkane is produced. So R and then CH2, CH3. This is a full reduction, if you like, complete reduction, uncontrolled reduction by the hydrogenation, the metal catalyzed hydrogenation reaction. So the corresponding alkane is therefore obtained. Okay, the corresponding alkane is obtained. This is uncontrolled reduction. Uncontrolled reduction. The hydrogen gas is usually used in excess. It's very, very difficult to stop the reaction at the alkene stage. Of course, we say the alkene because the alkene is viewed as an intermediate in this reaction, by the way. The alkyne can be reduced to the alkene, and the alkene can be reduced further to the corresponding alkane. So the reduction here is full, it's complete. The alkane, the corresponding alkane is obtained from a terminal alkyne if treated with hydrogen in the presence of metal catalysts such as palladium on carbon. If we take the same terminal alkyne, but now we treat it with a metal like lithium in liquid ammonia. Lithium is in group 1A. Lithium is in group 1A, okay, and in group 1A there is also sodium and there is also potassium. These are one electron donor. So we need a one electron donor. It could be lithium, it could be potassium, it could be sodium in liquid ammonia. And these conditions, by the way, are reduction reaction conditions that will reduce an alkyne, but it will not take the alkyne all the way to the alkane. The reduction is actually controlled. The reaction stops at the alkene stage. So the corresponding alkene is therefore, or rather, obtained. So this alkene is obtained if this or these conditions are used. This is called dissolved electron conditions, if you like. Yeah. Okay, and a group 1A metal, an alkali metal in the presence of liquid ammonia. Okay, these are the conditions. These conditions are used. The alkyne is reduced to the alkene. The reaction stops at the alkene stage. So this is controlled. This is controlled addition or controlled reduction. So this is one way to control the reduction if an alkene is desired from an alkane. Yeah? Because this is the typical, if you like, hydrogenation reaction conditions will take the alkyne all the way to the corresponding alkane. So this is one method or one way to stop the reduction reaction at the alkene stage. Another method to do this is to use what's called hydrogenation, yeah, or hydrogen, if you like, the use of hydrogen, but now not using palladium on carbon, but rather using what's called Lindlar catalyst. If Lindlar catalyst is used instead of BDC, then the reduction reaction of the hydrogenation reaction is controlled. The reaction stops at the alkene stage. So here also the reaction stops at the alkene stage, and this alkene is produced in a second method on how to control the reduction reaction of alkynes. Now, if you notice again, these conditions are similar to the hydrogenation conditions. The difference is the metal catalyst, and this Lindlar catalyst, you don't have to worry about much details, but this Lindlar catalyst is actually palladium that is deposited on calcium carbonate, which is treated then with quinoline and led to acetate. This is Lindlar's catalyst. You don't have to worry about much about details again. If you know this information, this is good for your chemistry knowledge. It is palladium that is deposited on calcium carbonate and then treated with quinoline and led to acetate. Yeah. Okay. So this is what basically prevents over reduction, if you like. Yeah. So this is what controls the reduction, and this is what limits the reduction reaction at the alkene stage. So an alkene is therefore produced if an alkyne is treated with either of these controlled reduction reactions, an alkali metal in the presence of liquid ammonia or hydrogen in the presence of Lindlar's catalyst. If the alkyne is treated with hydrogen in the presence of a transition metal catalyst, typically palladium on carbon, then the corresponding alkyne is produced. We discussed before reduction of terminal alkynes. Let's now discuss the reduction of internal alkynes. This is the general structure of an internal alkyne. And as we learned before, reduction can be of two types: uncontrolled, using hydrogenation reaction conditions, or controlled, using an alkali metal in the presence of liquid ammonia, or hydrogenation using Lindlar's catalyst. So if we subject an internal alkyne of this general structure to the hydrogenation reaction conditions, so hydrogen in the presence of palladium on carbon, the reduction is expected to take place all the way to the corresponding alkane. So the reaction does actually go all the way to the corresponding alkane, and the corresponding alkane is produced. So double addition of hydrogen to the carbon-carbon double bond results in the corresponding alkane. Okay. So this is uncontrolled reduction of alkynes. This is similar to the reaction of terminal alkynes with hydrogen in the presence of palladium on carbon. If we take an internal alkyne, but instead we react this with hydrogen in the presence of Lindlar catalyst. So if we take an internal alkyne, we treat it with hydrogen in the presence of Lindlar catalyst, then this kind of alkene is produced, and please pay attention that not only to the fact that the reaction is controlled. This is something that we knew before, that this reaction or this reduction is controlled. These are controlled reaction conditions. The reaction should stop at the alkene stage. That's what we learned before when we talked about the reduction of terminal alkyne. So also is the case here, the reaction stops at the alkene stage, but since the alkyne is internal, or since the carbon-carbon triple bond is not at the termini, then the alkene can either be cis or trans, which means the two R groups can either be on the same side of the carbon-carbon double bond or on opposite sides. In this specific reaction, or in the hydrogenation reaction, using Lindlar's catalyst, the cis alkene is actually produced. So cis alkene is produced if an internal alkyne is reduced with hydrogen in the presence of Lindlar's catalyst. Cis alkene is produced, the two R groups are on the same side of the carbon-carbon double bond. If the internal alkyne is instead treated with lithium or sodium, for example, in liquid ammonia, dissolved electron method, then again, the alkene should be obtained. This is the controlled reduction, as we learned before when we talked about reduction of terminal alkyne. So also here, the alkene will be produced, but in a complementary fashion, if you like, to the method which employs hydrogen in the presence of Lindlar's catalyst, where a cis alkene is produced. This method leads to a trans alkene. So this method is complementary to that method. A trans alkene is obtained in this case. So the trans alkene is produced. This method leads to the trans, while the hydrogenation using Lindlar's catalyst leads to the cis alkene. This is a very important observation. The two methods complement each other, which means if you want a cis alkene from an internal alkyne, then the reduction conditions should be hydrogen in the presence of Lindlar's catalyst. If a trans, on the other hand, a trans alkene is desired, then an alkali metal in the presence of liquid ammonia should be used instead. So now we will explain how does this reaction take place generally. So let's try to do a Cayley arrow mechanism. So let's just do that. If we have a carbon, this is the internal alkyne. Remember, group 1A metals are single electron donors. So single electron donors, which means they can donate a single electron. So we can take a single electron. This comes from, say, sodium in this case. So sodium can donate an electron, of course, to produce the sodium ion. Okay, so the electron will add to this carbon, and one of the pi bonds is broken like this. Okay, and please note the specific use of these Cayley arrows. Okay, this is single electron, so which means we should use the singly headed arrow to indicate movement of a single electron. This breakage indicates the release of two electrons. Therefore, the normal arrow, which means the normally headed arrow, or two-headed arrow, if you like, the normal arrow, which indicates the release of two electrons. If this is produced, then we will get, if this happens, then we will get something like this. Now we will have an electron on that carbon and two electrons on the nearby carbon. So this is an anion, and also this is a radical. This type of intermediate is called radical anion. So this is a radical anion. Now the radical anion will then abstract a hydrogen or a proton, if you like, from a proton source. In this case, it's ammonia. The proton source could be any other, like even alcohols, for example. But if we write ammonia as used in this reaction or in that scheme, yeah, okay, then the carbanion will be protonated like that. So the carbon with the negative charge abstracts a proton or a hydrogen in the form of a proton, and this hydrogen-nitrogen bond breaks simultaneously. Then this radical now is obtained, but this radical also is a vinyl compound. So that's why this radical is specifically described as vinyl radical. The vinyl radical. If you notice, we have one H has already been added, if you like, or has already bonded to one of the carbons of the carbon-carbon triple bond. So we have one H to explain its bonding with the other carbon. So for that to happen, this vinyl radical needs another electron, and that other electron should come also from another sodium atom that should be able to donate another single, or another atom should be able to donate an electron. So this electron will now add to this, so this will come now and it will add to that carbon to make an anion. And this anion is basically, or can be drawn like this. And this anion, by the way, this is an anion. This anion will adopt trans stereochemistry. So the two R groups will try to be as far away from each other as possible. So this is the origin of the trans double bond geometry action in this case. Yeah, it's the conformation, if you like, or the more stable trans conformation of the vinyl anion, which adopts trans geometry. So we can view it like this, yeah. So the two R groups will be opposite to each other. So this is trans vinyl anion, which adopts this geometry because it is more stable. So the trans vinyl anion is the source, if you like, of the trans, or the origin of the trans double bond geometry in this reaction. Now the trans vinyl anion then will pick up another proton from the proton source. So the anion will then come. It will take off one of these hydrogens from ammonia, and if that happens, already the two R groups, by the way, are opposite to each other, if you like. So this will lead to the trans alkene. Yeah. Okay. So initial addition to form radical anion. The radical anion gets protonated to form vinyl radical. Vinyl radical takes another electron from the metal to make a vinyl anion, which adopts trans geometry, which is then the source, if you like, of the trans double bond geometry. In this case, the trans vinyl anion undergoes protonation to lead to the final trans alkene product.